Welcome, scholars of Advanced Placement Calculus. Today we're going to be learning about limits. To start off though, you might want to know what is a limit. By definition, a limit is the value a function approaches as the variable within that function gets nearer and nearer to a particular value. That's a lot of gobbledygook, but maybe once we do an example you'll see it's not that hard. Alright, so for limits they can be broken down into categories: left-hand limits and right-hand limits. A left-hand limit, as given by the name, is if you were to look at a graph, you would find the limit as we look at it from the left side. So if we take an example function such that is f of x equals x squared, the limit of that can be found by finding 1.9, 1.99, and 1.999. As you can see, the f of x values get closer and closer to 4 without actually hitting 4. Similarly, we can look at it from the right hand side, if you were to see it from a graph that is. If you were to make a table of the values, as we get closer and closer to 2, with 2.1, 2.01, 2.001, we see that we get closer and closer to 4. An important note is if this happens, where we look at it from the left hand and the right hand, that they both are almost approaching 4, we can accurately say that the limit as f of x approaches 2 from the left hand and right hand side is 4. Another thing that should be noted, as seen by the examples here, a negative sign superscript above the x approaches 2 on the left hand symbolizes that it's a left hand limit, just as the right hand limit has a little power of a plus sign. Both those little positive and negatives indicate from which side of the function you are looking at.
Some of the basic rules for finding limits are shown above. These are just two, and there's a third we will show in a minute. But before we get into the rules, there is another way of solving limits than plugging each value into a chart. You can plug the actual limit, as we can see below. For instance, x equals a. We could plug a into the limit function to find the actual value that the limit will go to. So for our first rule, as we can see, our function is the limit of k, which is constant, times f of x will lead to our value, and that limit is from x to a. In order to break this problem down to make it a little simpler, we can move the k in front of the limit sign so that k won't have to multiply with f of x immediately. And this is what it will look like once the k has been removed from the f of x portion. And an example of this is if we have the function limit of 3 of x squared with the limit of x to the fifth, or x to 5. What we can do is we can remove this 3 from the x squared and put it in front of the limit function. So then what we would have is 3 limit x squared. We would then proceed to take the 5 that the x is going to, put that into the x squared portion. So then we would have 5 squared, but then it would multiply with the 3 afterwards. And this is much more useful in larger problems where you have multiple steps. As a second rule that we will be going over is if we have two functions that will both be going to the same limit value, so in this case x to a. The first limit is limit f of x equals L1, and then limit g of x would equal L2. Since they are both going to x to a, we could actually add them together. So we will have limit of f of x plus g of x with x going to a, which would result in us just adding the two together to reach our final value. In our example, we have limit x squared plus limit x to the third. And since they're both going to the fifth, we can combine them into one total function. And that function would look like limit of x squared plus x to the third to the fifth, to the power, not to the power 5, to 5. Then what we would do is we'd plug that 5 value into each x value, so we'd get 5 squared plus 5 to the third, resulting in 150. Third and final rule that we will be covering is the multiplication rule. So if we have two functions that both involve x approaching a, we can actually end up multiplying them together in certain cases. For our example, we have limit f of x equals L1, and limit g of x equals L2 as they both approach a. So what we can end up doing is we can combine L1 and L2 by multiplication to give us the final function of limit f of x times g of x, x going to a. Now for our example involving actual functions, we start out with limit, and this will be our full function here, and x will be approaching 5. And what we can end up doing is, to make this much more simple, we can split up the x squared plus 1 and the square root of x minus 1. And this will create two functions of the limit, where the limit of x squared plus 1 as x approaches 5 will be multiplied with the limit of the square root of x minus 1 as x approaches 5. And as we can see, as we progress further down, we will just substitute in the 5 for the x in the larger functions, giving us x squared plus 1 and the square root of 5 minus 1. We will ultimately end up with the answer of 52. And this is very useful, as I stated before, for breaking down very large functions and creating smaller steps.
Another topic that you will come across as you're finding limits is problems that consist of x approaching infinity. It's easier to see how this makes sense when you work through an example. For example, we have the limit as x approaches infinity of 3x plus 5 over 7x minus 2. Now if you follow what we told you earlier, you will get infinity over infinity based on just plugging in the number. Unfortunately, this is a non-removable discontinuity, as infinity is not a number but merely a concept. So what we can do, which also applies to all functions as they approach to infinity if you come across a non-removable discontinuity, is divide each term of the numerator and denominator by the highest power of x. In this case, the highest power of x we come across is x to the first. Thus, we break apart the function and take the second route as seen on the whiteboard. So we can take the limit as x approaches infinity of 3x over x plus 5 over x, all divided by 7x over x minus 2 over x, which seems like a lot of fractions, which can kind of be scary. But once you plug in infinity, we see that if we get a really, really small number over a big number, it accounts and is treated as 0. For example, in this case, if you put 3 times infinity over infinity, that's going to be a really, really big number and a really, really small number. When the small number is on top of the big number, it can be treated as 0. Thus, we can simplify that down using basic algebra, and we get 3/7 as the answer. A continuation of what I was saying before, as we have limits that approach that x approach infinity, here's 3 simple rules that are going to really help you out in complex problems. The first one, which says if the highest power of x is the numerator, as x approaches infinity, the limit is going to be infinity. Contrastingly, if the highest power of x is in the denominator as the limit of a function with x approaching infinity, it's going to be 0. Now, if we have a polynomial function with the highest power of x being the same in both numerator and denominator, we then resort to the ratio of coefficients to be your final solution to this problem. Last but not least, we would like to touch on the definition of derivative. The reason we learn limits at the very beginning of calculus is usually because the definition of derivative is defined as the limit as h approaches 0 of f of x plus h minus f of x over h is the derivative. Now, people go a lot more in depth with this, and you will learn further tricks which don't involve this much work. But for right now, this is just a simple lead-in to what you will learn in the future.